So in this video, we are asked to test the series for convergence or divergence, and we're gonna do a lot of these problems like this here. And I personally enjoy these problems. At first, they seem challenging, and you have to learn a lot of things before you can be proficient with it. But once you can be proficient with it, it's very fun. So my immediate kind of instinct is to take the limit. Okay, I just want to do that. I want to take the limit as n approaches to infinity. This is the divergence test. You have to check if this is going to be divergent or not. And the way you do that is you take the limit as n approaches to infinity of this thing here, and if this ends up being zero, then we are inconclusive. So it didn't help us. The divergence test didn't help us. But if we do get something that is other than zero, so anything other than zero, we can actually prove that this is going to be divergent. So let's go ahead and see if this gets us to something that is other than zero. This is just a simple infinite limit question. Notice that the denominator here is going to get larger at a faster pace than the numerator. And so that's the reason why we can conclude that this is zero. That's not the only reason. We could have divided by like n to the ninth power. So if we wanted to do that, we can take the limit as n approaches to infinity, and then divide everything by n to the ninth power, like this. If you really wanted to, that would just be 1, and then plus 1 over n to the ninth power. And this would get you to, of course, this would get you to 1 over n. And then if you go to infinity, it's going to be 0. This is going to get you to 0 as well, because, the denominator is getting large. This as well, and then so it's just 0 over 1, which is, of course, just 0. Simple as that. So that doesn't help you. So that was just a waste of time. No, it's not really a waste of time. It's good to check everything. Now, the next thing that you want to do is you want to move on to what else I can think about. Can I do like a telescoping series, for example? It might seem silly because you can't necessarily use a telescoping series here, but you just want to think about it. There's nothing wrong with thinking about it. We move into geometric series, no. Harmonic series, no. Divergence test we just did. Integral test, I wouldn't do that because it's not super easy to integrate this. It's not. So we have to move on. Let's go to P series. Can we use the P series here? Well, immediately I can't use the P series, but I do see these two terms that look like the P series can be used on them. But let's not worry about that because immediately I can't use the P series. Comparison test and the limit comparison test. So can I use one of the comparison tests? In fact, what I think about for the comparison test is, can I find a portion of this series that essentially is in the form of something that we already know, like a P series or a geometric. In this case, we actually see that's a form of a P series. So comparison test is looking like we can use it. Alternating series test, not really, no. Ratio test, I typically use that with factorials and nth powers. We don't have any of those here, so maybe not, but we still can see if the comparison tests end up failing. And the root test for series with nth powers, we don't have those here again. So that's probably our best bet here is probably the comparison tests. So I walked you through a lot of tests here for this one problem. It might be immediately recognizable to you that it's a comparison test. I won't be doing this for all of the problems. This is just the first one, so I wanted to do that. But again, let's look at this right here and use the comparison test. So what I'll do is I'll write out a new series as n goes from 1 to infinity, and I'll just take the n to the 8th power over n to the 9th power. What did we do? We essentially made if you want to use the direct comparison test, we can try. We made the numerator, we made it essentially greater because we removed the -1, so we made it greater. Oops. We made it greater, okay? So we made that greater. And then the denominator, we essentially reduced the size. We decreased the denominator. Effectively, this is going to be greater, that means, right? This is going to be greater than this. That's what I wanted to conclude. This is going to be greater than this. Now, this is basically, if you simplify, if you simplify, this is 1 over n, because that's n to the 8th over n to the 9th, and then if you subtract, you'll just get -1 and 1 over n. Now this is divergent. This is the harmonic series. This is the popular harmonic series with basically when p equals 1 for a p series. This diverges. It's good to know that. This here is less than that, and we can't really say anything about it using the direct comparison test, and so probably not the best thing to do. Okay, so let's not use the direct comparison test. Let's go ahead and use the limit comparison test. We can try to do that. So we know that this diverges. I'm just going to write that out. Diverges. So if we wanted to use the limit comparison test, what we do is we take the limit as n approaches to infinity of this, which is, we call that a sub n. So that's n to the 8th power minus 1 over n to the 9th power plus 1. And then we divide that by b sub n, which is essentially this. That's what we call b sub n. So this is 1 over n. So this would be a sub n, and this would be our b sub n. And so essentially we take the limit as b approaches to infinity of a sub n over b sub n. That's it. So if this is greater than 0, then we can conclude that this would be, well, let's not worry about that for now. Let's actually move on, and I'll say that in the end anyway. So let's go ahead and do some simple algebra here. So this would be the limit as b approaches to infinity. So what I'll do is I'll take this n to the 8th minus 1 over n to the 9th plus 1, and I'll just multiply by n because we're dividing by 1 over n, which is equal to basically multiplying by the reciprocal, so it's multiplying by n. This becomes, it's just it's a bunch of basic algebra here, but it's going to help you a lot because here we'll just have an n to the 9th. I'm just going to distribute this in like this, distributing it in. So that's just going to get you n to the 9th minus n over n to the 9th plus 1. What's this going to get you to? Well, again, this is to infinity, so this is actually not a hard problem. We don't need to worry about this minus n or this plus 1, because when we go to infinity, they're going to be irrelevant. And then we have n to the 9th and n to the 9th. Essentially, it's going to, if you think about it, we only worry about these two terms because they're the faster growing ones, but we have coefficients that are just 1. And so what we essentially do is we just take this coefficient over this coefficient and set that's just 1. So this is a very simple limit. Don't get confused. Review limits at infinity if you want to, or infinite limits if you want to get help on this. This is going to essentially tell you that this is greater than 0. What does this tell you? This tells you that since this is greater than 0, which means that it exists and it's greater than 0, whatever this series, whatever b sub n was, which is diverges, a sub n is also going to have the same result. So this would be divergent, or this also diverges. So what this tells you is if it's greater than 0, whatever result b sub n was, a sub n is going to have the same result. So if this was convergent, this would also be convergent. And so yeah, this is divergent, this is also divergent. So we end up getting to the conclusion of this is, so test the series for convergence or divergence. This is divergent, or the series diverges, and we are done. So we'll do more of these.